Okay, in this example, we're going to take another look at a two-sample proportion hypothesis test. A medical research study, forget this word two in here, a medical research study tested the effect of cholesterol-reducing medication. The researchers found that of the 4,700 randomly selected subjects who took the medication, 301 eventually died of heart disease. Of the 4,300 randomly selected subjects who took a placebo, as many as 357 died of heart disease. So when we're looking at this, we had a larger sample, fewer died of heart disease who took the medication, a little bit smaller sample, and we had more who actually died of the heart disease. We know right out of the gate that there was some kind of an effect, but we don't know if this is, whatever the effect was within the margin of error. So we're going to be testing to see if this is statistically significant. Okay, so at alpha of 0.01, and very often with medical testing, you use a higher or a lower level alpha or a higher level confidence level. Can you conclude that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? Okay, this is adapted from a Journal of Medicine. After we've done that hypothesis testing, we are going to construct a 98% confidence interval estimate of the difference between the two. Now, you're going to look at this and go, whoa, why 98%? Because we just said over here we had alpha of 0.09, which would be a confidence level of 99% for the hypothesis testing. But we are looking at this and we're checking to see if one proportion, sample proportion, was lower than the other. So that lower part tells us that we are going to be dealing with a hypothesis test in the tail. We're looking at the left tail. So we're correct with hypothesis test confidence level 99%, 0.01 alpha. But when we go to do our confidence intervals are two-tailed events. And so the confidence interval that is going to have 1% in each tail, including the left tail, would be the 98%. But that 2% outside would be 1% in the left tail, 1% in the right tail. So that explains the difference where we're going to use the 98% confidence interval and then the 99% confidence level for the hypothesis test. Okay, so we need to go on and identify our null and our alternative hypothesis and then go about calculating lots of different ratios. Okay, so our null hypothesis is that these two sample proportions are equal to each other, that there really was no significant effect of the medication. The alternative is that the medication was effective and lowered the rate of heart attack or death by heart disease. So we're testing to see the claim if that first sample proportion is lower than the second sample proportion. Okay, again, our confidence level is 99%. Our alpha is 0.01 for our hypothesis testing. This is a left tail test because we're testing to see if that first sample proportion is less than the second one. So it's a left tail test, and the z-score that correlates with that, or critical value that correlates with that, is negative 2.33. I would have gotten that going back to the activity that we did in class. Looking at this, 99% confidence level for testing would be 0.01 in the left tail, a z-score of negative 2.32. Now notice I'm going to go back to comparing to the confidence interval. Confidence interval is a two-tail test. The 98% confidence interval has 1% in the tail, the same z-score because there's 1% in that tail. But we're going to be using the negative 2.32 z-score for really both of these activities. Okay. Also, you could have gotten that from our statistics formula sheet. We're doing a hypothesis test. 0.01 in one tail would be 2.3. Back to the notes and all this calculating. So again, I like to have students do all their p-hats, q-hats, and their pooled proportions, sample proportions, all in one fell swoop, and then we start plugging things in. So looking at our sample proportion for our first study, that was the 301 died of heart disease out of 4,700 who took the medication, gave us this ratio or this percentage. The Q hat to that, these two are complementary. Okay, looking at our second sample, we had 357 who died of heart disease who took the placebo, the 4,300 who took the placebo. We have a little bit higher ratio here, so we're looking at these two or sample proportions. We can see that there's a difference there. Is it enough to be significant? That's what we're testing. And then our Q hat to go with that second sample would be the complement. Okay, when we're dealing with this, we have to also look at the pooled sample proportion, where we're looking at the total number of participants who died of heart disease out of the total number of people involved in the study. So we came out with this ratio. Again, it's kind of all in the pretty darn close here. And then our Q bar would be the complement. Okay, so we've got all of our pieces here. So when we go to calculate our test statistic, again, for the formula for the test statistic is a little more complicated than the original. I'll go back and show you where we would have pulled that. If you're not following it out of the notes, you would go to the formula sheet. We're looking at the z-test for difference of two proportions pooled, this long and involved thing here. Again, the formula for how to find the pooled sample proportion. And then also I want to point out that my Q bar, I use Q bar in my notes, and it's the same as 1 minus P bar. So don't be alarmed by that. Okay, so back to this. So we're plugging all of this information in. We get this long drawn out thing here. Now the zero comes from, if we're assuming that the population proportions are equal to each other, they would have a difference of 0. So that's why we're getting the 0 there. So when we plug all this in, we calculate, we get a negative 3.46, which is much smaller than our critical value of negative 2.33. When we go to look at each of our methods here, when I draw the curve here, I can see that, yeah, the test statistic is way down in that tail. That's in the rejection zone. When we do our p-value is much lower. This is the p-value that is associated with the z-score, the p-value that is associated with the z-score of negative 3.46, our test statistic, very low. So when the p is low, the null must go. So again, that tells us we can reject the null hypothesis. We go to do our confidence interval. We're plugging in the p hat and the q hats from what we calculated up here. So that's kind of long and involved, and I'll let you kind of follow that through just in the sake of getting this video finished in a timely manner. I plug all of this in, and I end up with a confidence interval where both values are negative, and that kind of seems weird, but yes, we could have these differences being negative here, that the one really is smaller than the other, so when you take the other away from it, you end up with a negative value here. That's why that happens. But also I want you to recognize that both of these are in the negative zone. 0 is not involved in this. So 0 cannot be in this interval. The difference between these two, the population proportion of those who took the sample or took the medication who didn't, the difference can't be 0 because 0 isn't involved in our confidence interval. So again, that's going to support our decision to reject the null hypothesis. There is enough evidence to support the claim that the death rate is lower for those who took the medication. In other words, it's significantly different, statistically significant. Okay, I know you want to do this on StatCrunch, so we're going to open up StatCrunch. I'm going to move this down here. I need to make sure that we can get all the information here. Okay, we're going to go into stats, down to proportion statistics. We are doing a 2-sample with summary. It's going to open up and we can put all of our information in here. Looking at our first sample of those who took the medication, we had 301 who took the medication, who died of heart disease out of the 4,700 who took the medication. Then in the second sample, we had 357 who died of heart disease out of the 4,300 who took the placebo. Okay, so our hypothesis test is automatically defaulted. We have the difference is 0, but this time we're going to say that the first one is less than. That's what we're testing to see if the first sample proportion there who took the medication, if that ratio of those who died of heart disease is less than those who didn't. That's why we're doing the less than. So we're going to hit compute. We end up with the same information that we had here. Oops. Our test statistic came out to be, sorry, I'm trying to get this all on the same screen. Negative 3.46, which we have here. Our p-value was the 0.003, which we have here, very, very low. So again, that supports what we came up with earlier, but I want to go back and do the confidence interval, so I'm going to hit edit. Same information as far as our successes and observations for sample 1 and 2, but again, I need to change gears, click that I'm doing a confidence interval, but this time I need to tell it that I'm going to choose a 98% confidence interval because that is the interval that will have 1% in each tail. We go to click that and we find that we have the same the same lower limit and upper limit that we calculated when we did this by hand.